Okay, so last time we ended on calcium, correct?
I don't remember.
Help remind me.
I have no clue.
I know, you don't know. Close
Or
it up. Close it up. You're gonna listen to
Probably
chemistry
was.
today.
Because I remember thinking we didn't get to the,
We didn't get to Scandium.
yeah.
This is the last one I think we did, right? Coming out. Okay. Now, as a little bit of review from what we covered last time. So as we saw, we've got our different energies that we would see on our graph. So these electrons right here, those would represent the first energy level. And there's only two of them, right? And then these two would represent the first energy level, the second energy level, S. These would represent the second energy level, P, 6 electrons. These are going to represent the second or the third energy level, S. These are going to represent our third energy level, P. And with calcium, we get to the fourth energy level, and those will represent the fourth energy level, S. So every energy level has an S sublevel. Every energy level starting with the second energy level has a P sublevel. Now, first energy level has one sublevel. Second energy level has two sublevels. How many sublevels will the third energy level have? As we said, 3. How many sublevels will the fourth energy level have? How many will the 10th energy level have? 10. So the number of the energy level value, the energy level number is going to tell you how many sublevels you have for that energy level. Each sublevel will hold a different number of electrons. Okay? Where am I writing a 2s? To the right. A significant amount, right? Okay, because there's a big change between our first and second energy levels. So I'm going to draw the 2s here. Where's 2p go?
Barely to the right of.
Go to the right.
A little bit to the right. Not a big difference though, right? It's not a new energy level. How tall does it have to be though?
Way
6. It has to be 6.
Be specific. 3 times. Because the P holds how many electrons?
6.
And the S holds how many?
2.
2 times 3 is 6. I think if I'm not mistaken, it goes all the way to the top. Is that correct?
Yeah.
Oh, that's a terrible line. It's better. So that's the 2p. Now what? What comes after 2p?
4.
Where?
Or wait, yeah, 3. To the right.
A
Significant.
little bit or a lot? Where's 3p go?
Right now, go to the right.
3 times as tall. Good. And where's the 4s going to go?
To the right. To the right.
Who's got questions?
Why didn't the third energy level have a third sublevel?
Good question. We don't need it yet. So, for those of you over here that didn't hear the question was, why didn't we use a third sublevel? So, a lot of time, well, most of the answers are on the Periac table. Everybody look at the Periac table. Now I know yours does not have it. But if you look at the one up there on the sidewall, we see that it's got numbered to on the left-hand side, 1 through 7 down the left-hand side. And those numbers represent the energy level, the highest energy level. Okay? So when we get to calcium, its highest energy level is going to be the 4th energy level. The other thing to note, and I think we did this last time in class, is that the first 2 columns, and it kind of blends in, but above here, there's only 2 columns here. We'd actually go up and down all the way. This represents only 2 electrons. So this represents what sublevel?
S.
Yes, because it only has two electrons. And if we look at how the periodic table goes, so if you went across, that'd be 1s. Helium actually technically is part of the S. Okay? And there are periodic tables that will have helium here. Most have helium here because it acts like these elements. But after the 1s comes what? Look at the board. 2s. Well, that's the 2s, right? What comes after 2s?
2p.
This is the 2p. We've got 6 columns here because the p sublevel only holds 6 electrons. Everybody okay? And we can continue after that. So after 2p comes what? 3s. After 3s comes?
3p.
After 3p comes?
4s.
4s.
Then
So what are these? Yeah,
3d.
these are the 3ds. That's where our sublevel comes from. Now the reason why we don't get that 3D yet is because, and this is really important, conceptually, electrons are going to arrange in an atom to make the lowest energy possible. Okay? So remember, our potential energies are negative, correct? And the magnitude, we've talked about them as an attraction, but they are an energy. And the more negative the energy, the lower the energy it has, right? Because it's a negative value. I'm going to wipe this because I need to. Actually, I don't want to do that. Now, if an electron is really, 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 really far away, what is the energy? The potential energy? If they're really far away from each other, potential energy is equal to what? Essentially equal to what? 0. So if my x-axis here is distance, if I'm really far away, I'm going to be essentially 0. I'm going to change colors. No, I don't want to do that. Crap. As it gets closer, what happens to the attraction?
Gets bigger.
The attraction gets bigger, but the numerical value gets what? Because it's a negative value, that's meaning the attraction. Okay? The magnitude of which is larger, yes, but it means it's a smaller number. And this is where we start talking about the energy. Just the energy, not the attraction, the energy. The energy gets lower, correct? Now, this is just for one electron. So if I had a whole bunch of electrons all interacting with each other and repelling each other, the value is still going to be negative, but it's not going to be as negative if it was just the protons with the electron alone. In the end, though, it's still going to be negative, the potential energy. And our goal in nature, the goal in nature is to have a value that's as low as possible. So when we are looking at an atom that has multiple electrons in it, we need to take into consideration that I did this last week. It's frustrating. We need to take into consideration that the electrons are going to repel each other. That reduces the attraction somewhat. If I have electrons in the third energy level, in the S and P, and we know that it's got another sublevel, and adding that electron to that sublevel increases the repulsions more than if we add it to the 4s, then that electron's going to go to the 4s. Because we want to reduce the repulsions within the atom as much as possible. That way it can be at its lowest energy state as possible. So in this case, the electrons go into the 4s before we enter and use the 3D, because that's what it's going to be called, third energy level D, to reduce the amount of repulsions. Okay? So scandium. We get a new peak. So calcium, oops, too far. Calcium had 6 peaks, right? The 4s, the 2s, the 2p, the 3s, the 3p, and the 4s. Scandium's going to now have 7. Where is that 7th peak going to go? Draw it on yours. We did this last week, right? With the phosphorus and argon. So you're overlaying stuff. Did I have you guys do the screen thing last week?
Yeah.
Okay.
Do you want us to do it again?
Yeah, but I'm going to call on you randomly. Bob. You can put yours up. Jack, you're going to be the next one I call. So I have it ready to go. Go ahead and put it, go ahead and enter in the code and stuff to allow me to accept it. Good. Zoom out. Because I think on this, I'm intended for you to
Do the other.
do the others as well. So where would let's where would they all be
To the left.
shifted to the left? Okay. Go ahead and draw those in real quick. And then it'll have to be, like I said, it doesn't have to be anything perfect or beautiful. Now what I would tell you to do here is move that 3D over just to the left a little bit. That way it gives you a little bit of room to put the 4S in there. Okay, so that's what it would look like. Okay. Ananya?
For the last one, would you put 4S before 4P or
So are you saying have the 4S to the left of the 3D?
is it?
So this is the 4S here with 2 electrons, and this is going to be the 3D. Okay? So the 3D would be to the left of that 4S.
Would the 3D be closer to the 3P and the 4S?
Actually, surprisingly, no. And that's where we're just going to have to. What happens is as we get these other sublevels, they do have they're closer to the next energy level than what we were seeing with the second and the third. Well, actually, in this case, the third is starting to get closer with those higher sublevels. Okay? And that's what, that's where we got to use that term energy level to define an area, a range of values. In the end, those electrons that are in 3D are closer to the nucleus on average than what the 4s is. Okay? Who's got questions? Nanya? I can't hear you.
How do you know what to use 3D?
When to use 3D?
Yeah.
You look at the Periac table. When do you use 3Ds? Roll those. Okay? Because, and this is what, so remember earlier I said that the 4 on this represents what? It does represent the fourth energy level, but it represents the highest energy level for that row. So the highest energy level is going to be for the 4s and the 4p. These, though, are 3s. Okay? We would designate these as 3D electrons for these elements. Because that's the sublevel that they're in. I got 2 questions for you, Nanya. So, well, 3 questions, actually. Ready? So after 3D comes what? 4P. After 4P comes what?
5S.
5S. Good. After 5S is going to come what?
4D.
Did you say 4D?
Yeah.
Absolutely. Answers are on the table, right? You just need to know how to read the table. You haven't been told how to read the table until this class, correct? Okay. Good. So you just follow. It's just patterns. Bella?
How many electrons can go into the D?
You tell me how many electrons there can be in D. Look at the periodic table. 10. Because that's how many columns.
And when you write out them on the graph, would you put electrons in 3D before you go into 4P?
Yes. Yes. So when you put, yes. Because we don't get to the 4D or 4P on the periodic table until after we get those 3Ds, right? Okay. All right.
I think you need to stop me.
Okay, so your 1S, 2S, 2P, 3S, 3P, 3D, 3D, and 4S. Who's got questions? Who's got questions? Anybody? Emerson?
Wait, can you explain again why electrons go into the 4s before they go into the 3D?
To reduce repulsion. So, even though the third energy level, for those of you over here who didn't hear the questions, why do the electrons go into the 4s before the 3D? And it's to reduce repulsions. So in calcium, the arrangement of electrons has the lowest energy, the least amount of repulsion, most attraction. That corresponds to lowest energy. Okay, because remember, the energy, the V is equal to a negative value. And the lower the value is, the greater the attractions. So it has the lowest energy, least repulsions when it has electrons in the 4s rather than the 3d. If you think about it, it's kind of like your sub-level, the energy level is getting full. It's getting a bunch of electrons. It's already got 8. Okay? Repulsions are starting to increase. And having the electrons further away in the 4th energy level reduces the amount of repulsion that would occur compared to if you had the electrons in the D, which would be closer and repelling more with the other 3rd energy level electrons.
Well, wouldn't there be a bigger attraction since they're closer to the nucleus?
And that you're right, but, and this kind of goes back to the question you had earlier. Remember, this D is already really close to the 4th energy level. So, you're right. The electrons being closer in the 3rd energy level would have a greater attraction to the nucleus because they are closer, but you've increased the repulsions because there are more electrons in the 3rd energy level. And that's the trade-off there. Having them further away reduces the amount of repulsion in total. And that's why it takes the arrangement it does. There are other factors involved as well. Okay? What we're focused on are those factors that at this level of chemistry we can explain using some reasoning and stuff. But it does have to do with the repulsions of those electrons. Okay. So now we're ready to take our next step. So the scientists are very well aware of how the electrons, or at least in terms of the spectrums, the energy states that the electrons take. Okay? Now, they are working really, really hard at trying to come up with a coherent model that can be applied to all of the atoms on the periodic table. And one of the first people to make look at this from a different perspective. And that's one of the keys here in science in general. Sometimes to make progress, you just have to look at it from a completely different perspective. And de Broglie, that's how you pronounce that, he looked at the electrons and everything that was being studied about them and said, all right, electrons are particles, but they have wave properties, just like light does. They've got frequencies, they've got energies, okay? Because of that combination, he goes on to explain further why the electrons just don't fall into the nucleus, because that's one of those like lingering questions out here. If the electrons are attracted to the nucleus, why don't the electrons just go and get closer and fall into the nucleus? And de Broglie explained it that the electrons have kinetic energy. And that kinetic energy is related to the area that they are existing in. The smaller the area that you're existing in, the higher the kinetic energy. So if they get closer to the nucleus, they're just going to go faster and faster and faster. And that's what essentially keeps them from falling into the nucleus, because what's the fastest anything can go? Speed of light. Schrodinger builds on this. And basically what he does is he treats the electron as if it were a wave only, not a particle. Now we do know, again, I gotta reemphasize, electrons are particles. They have wave properties. But in the atom, the best way to describe the electrons is if they had a wave only. And we saw that light has, energy. It's got a wavelength, so on and so forth. So the energies that the electrons can have are going to be related to waves. Did I do the little sphere with dots?
Yeah.
Okay, so because I was gone on Wednesday last week, my period 1 class was a little bit off from where you guys were at. Okay, so Schrodinger looks at the location, quote unquote location, as a probability. That's what I did last week with with the sphere and the dots. Okay. Part of that is uncertainty, and the uncertainty is the size of an atom. So we know the electrons in there. We know the electrons have a certain amount of energy. And Schrodinger's equations describe the area of probability with a little bit of uncertainty about the size of the atom it's in. So we can never really say exactly where an electron is. What we can do is say where the electron is most likely to be found. It's kind of like in this class, if you guys are electrons and the school is the atom, if the dean's looking for you, where are they going to look first during period 1? I'm sorry, during period 6? In this room. Are you guaranteed to be in this room during period 6? No. Take Sam, for example. Sam, you're down in the CGTV room during the first 5 to 10 minutes of class. So, does that make Sam not part of this class? No, Sam's part of this class. It's just her location is different than what we have. Okay? If I want to find, Adam, more likely he's going to be right there. But it's not a guarantee. Do I have any athletes in here? Okay. So, let's say they call you up to the athletic office. For some reason, okay, they say, "Hey, can I see, Emerson?" And Emerson goes up, and it's the middle of the period. Is Emerson still part of this class, even though she's at the far reaches of the school? And if you don't know where the athletic office is, some people don't. It's up by the Math West Gym, by where you exit out the buses. That's where they do buses still, right?
Yeah.
Okay. So, and here's the thing. Weird enough, the energy. So we associate a specific amount of energy to an electron in a sublevel, right? Well, if this classroom is the sublevel that the people you guys are supposed to be in, no matter where you're at in the atom, the energy is still the same. Okay? So, yes, distance is a factor, but distance isn't the only factor. That falls under the many other aspects well beyond the scope of this class. Okay? Now, Schrodinger's equations weren't really able to be solved until the 1960s when we had the first supercomputers. And what a supercomputer was in the 1960s is nothing compared to what you guys have in terms of the supercomputer sitting in front of you. Okay? So your phone, your iPads are magnitudes faster and more capable than the computers they had in the 1960s. But there were limitations. To be able to do the calculations that Schrodinger's equations described by hand were impossible to do because of the the large number of possibilities. So, Schrodinger's equations have three parameters that describe the electron. Okay? And basically what the result of those calculations is a three-dimensional shape. Because atoms aren't flat. Atoms are three-dimensional. We'll talk about this a little bit more here in a little bit. Now, we've already touched on some of these. Okay? So, we have an energy level. And the energy level, the principal quantum number, that's what it's called, that's that number that we had running down from top to bottom on the left-hand side. The symbol for it is N. I'm not overly concerned about that. So, a couple of things it tells us. It describes the range of possible energies that an electron can have. Okay? That's our sublevels, right? So in the second energy level, there is not one specific value, there is a range of values. In the third energy level, there's a range of values that are different than the range values for the second. It determines the area of probability. So in the first energy level, the area of probability is really small. And again, it's one of the things people that are watching this aren't going to be able to see. No, I think this. If that's my second energy level, I'm sorry, first energy level, then my second energy level is going to be, oops, crap. Simply bigger. Okay? It's still going to be spherical overall for the most part, but it's simply going to be bigger. So my area of probability, the area, the volume that the first energy level takes up in an atom is going to be smaller than all of the other areas. Second energy level, bigger. Third energy level, even bigger. Oh. You get the idea, right? So atoms are like ogres. Ogres are like onions. They got layers. Okay? Questions? And we've also talked about this. Except for the first energy level, every energy level has multiple sublevels. How many? Equal to the number of that energy level. So the first energy level has one sublevel. The second energy level has two sublevels. The third energy level has three sublevels. So on and so forth. Jackson?
Good question. Will the energy level ever determine the position, like having 1s?
Or is it will
Not-
the energy level determine position?
Okay, say it again, because you lost me there for a second.
What energy level determine position?
Always. Always. And when position by position, are you talking about the peaks? Or are you talking about the location of the electron in the atom? Yes.
All right.
So, remember last time how we said that, in the first energy level, when I put all the dots on the screen and I drew the circle, right?
Yeah, I forgot we did that one time before last time.
And we said that the average distance, okay, so if we look at all the possible locations,
Yeah, I remember that.
there's going to be a certain distance away from the nucleus that we can say that they're most likely to be found. When we looked at the second energy level, we saw that when I put the dots up there, they overlapped with the first energy level because the electrons in the second energy level can be as close as electrons are in the first, but that's not where you're most likely to find them. You're most likely to find them at a distance further away from the nucleus in the first energy level. Okay, and that kind of goes back to the example I used with people in where they're at in relation to this room. Even though you're part of this class, you may not be in this classroom. Doesn't mean you're not part of the class, though. Does that help? Okay, so here are the sublevels. The S sublevel is a sphere. The P sublevel is not a sphere, but when you look at it overall, it's hard to see a sphere, but it's kind of spherical. D orbitals, or D sublevel, that's got much more of a sphere look to it when you look at it in total. Now, as we've said, each energy level has an extra sublevel. So when we get to the fourth energy level, we're going to have an S, P, and D. The fourth we're going to call F. Look at the periodic table. Where is the F sublevel going to be located? Jackson?
The bottom one, like 57.
The very bottom. The parts usually are separated apart on the periodic table. Be careful with this, please. I'm going to pass this around. This is what's called the long form of the periodic table, and you'll see that it puts those in where they should go.
The F orbital would be 58 through 71.
Yeah, so these two right here, every periodic table is a little bit different. So these two actually would fit up here.
Yeah.
That's why I've got this red piece of tape here. These then are going to be part of the F. Now on your periodic tables, the purple periodic tables, that's what you have it like this here, right?
Yeah.
So I think if you counted the columns on this at the very bottom, count them.
14.
Is it 14?
Well, if you count,
It's 15.
if you count 57.
But, so it's like this one here. These fit here. Okay? Jackson?
Does that mean 14 electrons contained in that area?
Yep. So the F sublevel has 14. All of them are even in number. And there's a pattern. 2, 6, 10, 14, they're all going up by what? So even though we don't have it, the next sublevel would hold how many?
18,
18.
then 22.
And 22, and 26. I mean, there's patterns here. There's patterns. Keely?
So if LA and AC aren't F, then like
They're not. They're part of the D.
oh, so they're D.
Yeah.
Okay.
Yeah.
Got it.
And that's why, basically part of this is teaching you how to interpret the periodic table, right? The representation on the periodic table is this. Who's got the little periodic table and passed around? I need to see some on it. So when you look at the periodic table, now look at it thinking of these sublevels. Each part is representing the electrons there. Okay? I know the middle, you guys here in the middle haven't seen it yet. The reason why we don't use, or actually we'd use it, the reason why you don't see periodic tables like the one that's going to come around is because it's too long to fit on an 8.5 by 11 piece of paper. So putting those down at the bottom makes it easier to fit in a format that's usually what book size is. So that's called the short form, and that one's called long form. I think they've seen it. Have you guys, you haven't? Okay. Jackson? What's that? More of it's yellow?
You said helium.
Oh, helium's yellow?
It's because
yeah, that's why I wanted to look at it, because I didn't know where they had it. And that's one thing on that thing I would change. I would actually put helium, if they're going to put it together like that, I would put helium above beryllium, because that's where it fits numbers-wise better. And that's what, little details like that, you can't, periodic tables can be designed for a specific purpose, for quick reference. The periodic table that we use is kind of general purpose. But you can have periodic tables that have, different arrangements and structures, all very similar, with slight variations due to what their use is intended for.
Why do we put helium over there?
So, one of the most important parts here, and something I haven't really mentioned, is that all of the properties of the elements depend on their electrons. So, if one atom is going to interact with another atom, where do they interact? At the valence shell. And so, on the periodic table, the properties of the elements depend on that arrangement of their electrons. So, on the periodic table here, except helium, because it can only have 2 electrons, all of these have 8 electrons in the valence shell. And in the valence shell is always going to consist of S and P, which is how many? 8. And your teachers in middle school, some of them might have taught you about an octet, right? That's where the 8's coming from. We would consider helium to have an octet because an octet simply means that its valence is filled. And all of the electrons that have their valence shell filled are going to act in a similar manner. That's why lithium, sodium, potassium, rubidium, cesium, francium, they're all in the same group because they all have the same properties or similar properties, not exactly the same, but they're all very similar to each other because they all have similar configurations. All of them are going to have how many electrons in the S sublevel? Not lithium, sodium, just one. Because they're in the first column of that. Beryllium, magnesium, calcium, strontium, they all act a little bit differently than lithium, sodium, potassium because they have how many? 2. And they all are going to act very similar.
I think we need to get a new set of slides.
Oh,
I'm pretty sure.
did that the one to end after that one? Did you guys have, so the one with the periodic table with the S, P, D, and F? Okay, so go into Drive, and when I printed it off, I must not have printed all the slides. So I have a document titled Missing Slides or something like that. You guys see that or no?
I see 2 atomic theory 8.
There's two, yeah.
This is the one we did, I think.
Go back to the other one. Or did I do all of the slides?
Missing
slides.
Missing slides.
Yeah. The one that says Mising slides, I guess. Oh. Switch to list view and not box view, and you'll see what I'm talking about.
There are 2 things that say 8.
Do I not have the?
I don't. Yeah, that's.
So I don't have that on there?
No.
Oh, for crying out loud! Hold on. Okay, so what's the last slide you guys had? This one?
We had the one with, yes.
That's the last slide?
Mm-hmm.
Crap.
And then missing slides, or missing slides, we have electron configurations for ions is our first slide.
Delete what you guys just opened up from Notability if you opened it up there. Okay. Refresh your drive.
Oh, it says missing slides now.
Yeah, I changed.
Okay.
You should say have one that says missing slides, and it should start off with this now. Start.
Got it.
We're good? Okay, we're good now. All right, thank you. Okay, so orbitals. Orbitals, sublevels. So just like we said, energy levels, they've got sublevels. Okay, so the second energy level has 2 sublevels, S and P. Third energy level has 3 sublevels, S, P, and D. Fourth energy level will have how many sublevels, class?
5.
Fourth energy level has 4. And what are they? S, P, D, and F. Okay. We can further subdivide the sublevels themselves. Now, this is something we do not see in the spectrums that we saw. This comes out of the equations that are way beyond what we're going to cover in this class. But in the model of the atom that we use, the sublevels themselves get chopped up into smaller pieces. Each piece can hold 2 electrons. Okay? Now, the first energy level has an S sublevel, and that S sublevel is only made up of 1 part. they can hold how many electrons?
2.
2. The P sublevel can hold how many electrons?
6.
If each part of a sublevel can hold 2 electrons, how many orbitals is the P going to have?
3.
3. If you can't remember that, go to the periodic table, count up. I mean, you're going to have to know something. You're going to need to know where the S, the P, D, and F block are on the periodic table. But if you know where they are, then all you got to do is count. And then divide by 2. 1, 2. That's the S sublevel. How many orbitals?
1.
1. Because 2 divided by 2 is 1. I got 6 columns. So my P sublevel can hold 6 electrons. Divide that by 2 and you get 3 orbitals. Each orbital can hold 2 electrons. How many orbitals for the D?
5.
And for the F?
7.
1, 3, 5, 7. See how they're going up by 4? Remember what we said earlier? There's patterns. It's just patterns. Okay. I don't want to dwell on this too long, but back in the, 2009 is when this was published? This isn't stuff that people just discover and then leave alone. They continually look at these things to help refine them. But back in 2009, a group of scientists used new technology, new then, we're even better now, to identify and look at what the orbitals would look like. And remember how I said you should put a bunch of different dots to represent where the location of the electron is? That's what this is. They're measuring the location, quote unquote, location of the electron over time. And notice how it gets fuzzy out here, right? These areas out here, that doesn't mean that the electron can't be there. It's just not there very often. Where is it mostly? In here someplace. The p orbitals. If you go back and look at the p orbitals, you'll see that each orbital had 2 little lobes on it, right? So each one of these represents an area where 2 electrons can be. And that's what we see with this. This represents a p orbital.
Do electrons, all electrons go at the speed of light? Or-
Close to it. Close to it.
So when they like take the microscope, it shows like where they are most likely going to be.
They're registering a location at one instant in time. If that makes sense. Because they don't know where it came from and they don't know where it's going, but they know at that point in time it was there. They're just doing this multiple times, gazillions of times, to get these. Now, I know I said earlier that Schrodinger's equations included 3 variables that describe the location of the electron, but there is actually a 4th called spin. Because electrons have to be something a little bit different about the electrons for them to be in the same orbital. I'm not overly concerned about what spin actually is. Okay? But it's a property that the electrons have unique to that electron. The spin of electron can be changed. It's not a permanent thing. It's not like charge. The charge of an electron is negative. That can never change. The mass of an electron is set. That cannot be changed. The spin of an electron, that can be changed. Now, I'm going to be able to switch back to this slide so that we can look at how we do electron configurations. So I'm going to I'm going to insert a slide here. Add slide that's blank. Yeah. Okay. Somebody pick. Pick an element between numbers 19 and 53. Jackson?
Chromium.
Which one?
Chromium 24.
Chromium? Okay. So what I'm going to show you here is what's called orbital notation. Now if you can do an orbital notation, you can do what's called an electron configuration notation. And what we do with this is we symbolically represent the energy levels, the sublevels, and stuff. So chromium has 24 electrons, correct? Where are the first 2 electrons going to be located?
1s.
In the 1s. So we designate 1s. We put a line above that, and that line represents the orbitals. How many orbitals does the s sublevel have? 1. How many electrons can go in that s sublevel? 2. Now, this is where the spin we represent like this. We just use arrows. Up spin, up down spin. For 2 electrons to be in the same orbital, they must have opposite spin. You cannot have 2 up electrons in the same orbital. Same thing. You can't have 2 down electrons in the same orbital. Once we fill up the 1s, what comes next?
2s.
And this is where we kind of follow the periodic table. So if you follow the periodic table, we go through, put your finger on hydrogen and go over to helium. We just went through the 1s. What comes after helium?
Lithium.
Lithium and beryllium. And since we've got 24 electrons, 2 electrons are going to go in that s, the 2s. So we'd have this. Is everybody okay so far? After 2s comes what on the periodic table?
2p.
2p. How many lines for the 2p? How many orbitals can it have?
3.
3. So I'm going to put 3 lines. Each line represents where 2 electrons can go for a total of how many?
6.
Everybody okay? After 2p comes what?
3s. 3s.
How many lines to represent orbitals?
1.
How many electrons?
2.
Everybody all right? After 3s comes what?
3p.
You guys are following along on the periodic table, right? So 3p, p can hold 6 electrons. It's 3 lines to represent the 3 orbitals. So far I have drawn 10, 12 electrons, 13, 14, 15, 16, 17, 18 electrons. Still need to get to 24, right? Everybody doing okay so far still? Jackson?
What do the arrows represent again?
Say again?
Arrows represent.
The arrows represent the spin. So electrons have a property called spin. Again, I'm not overly concerned about the details of that. But for 2 electrons to be in the same orbital, they have to have opposite spin.
Okay.
So you would, here also, what comes after 3p?
4s.
Wait. Yeah, well,
You're thinking 3D, right?
yeah.
And actually, there's two different ways of doing it. I'm going to stick with this way because periodic table just simply makes sense. I'm going to do this. So Jackson, you could not have that. That would be incorrect. Okay? They have to be opposite. Okay, look at your location on the periodic table. We're in the same location right now as calcium, correct? What comes after 4s?
3D.
3d. How many lines for 3d?
5.
5. So we represent all of them, even though they may not be filled in. Okay? Now, I call this a bus seat rule. You're getting on a bus, you know nobody on that bus. You've got people sitting in seats with empty seats next to them, and you've got empty seats elsewhere with nobody sitting next to anybody else. Where do you naturally tend to go?
Without anyone else.
Without anyone else. Jackson?
So does every electron go its own line?
How many of them?
One.
Where's chromium at?
Chromium 24, so maybe it's 4 of those. So it'd be one empty one still.
And that's where we would stop. If you count up the number of arrows that we have 24 arrows to represent the 24 electrons. Why would it not be beneficial for this? Jackson?
And there'd be 3 empty ones. How does that mean empty?
Not just because they're empty though. Bella?
To lower the repulsion.
To lower the repulsions. If they're in the same orbital, they're in the same general vicinity as each other. Whereas if they are in different orbitals, there's not as much repulsion. Which gets back to what drives all of this, people?
Energy?
Energy. And energy is affected by two things. What are they? Things we've been talking about from the very beginning. One starts with A.
Attraction and repulsion.
Attractions and
That's what I
repulsions.
thought, I just wasn't sure.
I mean, the reason why, so Bella just got done telling us that it's going to be one in each because of repulsions, rather than having two of them in two slots.
Quick question. So the spin rule does not apply to that because there's no other electron?
Correct. So it can, well, okay, so if you go back and look at your rules here. One electron in each orbital before two because of repulsions. All electrons in half-filled orbitals are going to have the same spin. So I drew all of mine with up spins. You could draw them all with down spins. Okay? Questions?
Could some of them be up spins and some of them be down spins?
No.
Okay.
Not until you pair them.
Okay.
So if they're not paired, If they're like what we had with the one, if they're not paired, they're all going to be the same spin. Okay? Now, there's a shortcut to this. I know you guys love a shortcut. The shortcut is this. Ugh, really? You had to do it now. Hold on a second. A shortcut is this. What's the previous... Okay. You guys know what noble gases are?
Yes.
Group 18. Okay, so the previous noble gas to chromium is what?
Argon.
So what we would do, oops. Is we would put argon in brackets. So this is for chromium. We put argon in brackets. And what that does is it takes care of all of the electrons through argon. So we don't have to write it. What comes after argon?
4s.
4s. So then all we do now is just this. And after 4s is
3D.
4d.
That's it. That's all you'd have to write compared to what we had before. Are you okay with that? Now, the other format, I'm going to just write this real quick just because of time. So with chromium, we could represent the electrons using what's called electron configuration. This up here is called orbital notation. What I'm going to show you here is electron configuration. And then rather than showing the orbitals and spins, because usually that's not something we're concerned with, we just want to know how many electrons. How many electrons are there in the S? Class, how many electrons are in the S? So we just put it as an exponent. Second energy level, S.
2.
After 2S comes what?
2p.
How many?
6.
After 2P comes?
3s with 2. 3d with 6. 4s with 2. 3d with 4.
And 3D with 4.
For chromium. For chromium.
For chromium, 4. Okay. And what's the shortcut for that?
Noble gas. Noble gas again?
No gas. So AR, 4S2, 3D. Okay. In Canvas, you've got links to, it should be active now, but if they're not, you have ALs. You cannot access them through Canvas, go directly to the AL system.